So our administrative points for today, assignment 3 is due tonight. So who's done? That's good. Was it easier than assignment 2? Okay, that's good. Hopefully gives you more time to work on your projects. So also remember your milestones were turned in last week. So we're in the process of looking through the milestones to make sure those are okay. And also we're working on assignment 2 grading. So we should have that done sometime this week or early next week. Last time we had a whirlwind tour of all the common software packages that people use for deep learning. And we saw a lot of code on slides and a lot of stepping through code. And hopefully that you found that useful for your projects. Today we're going to talk about 2 other topics. We're going to talk about segmentation. Within segmentation there are 2 subproblems, semantic and instance segmentation. We're also going to talk about soft attention. And within soft attention, again, there's sort of 2 buckets that we've divided things into. But first, before we go into all these details, there's something else I want to bring up briefly. So this is the ImageNet classification errors. I think at this point in the class, you've seen this type of figure many times, right? So in 2012, AlexNet, 2013, ZF crushed it. Recently, GoogleNet, and later ResNet is sort of won the classification challenge in 2015. But turns out, as of today, there's a new ImageNet result. So this paper came out last night. So Google actually has now state-of-the-art on ImageNet with 3.08% top 5 error, which is crazy. And the way that they do this is with this thing that they call Inception v4. This is a little bit of a monster, so I don't want to go into too much detail. But you can see that it's this really deep network that has these repeated modules. So here there's the stem. The stem is this guy over here. A couple interesting things to point out about this architecture are actually they use some valid convolutions, which means they have no padding. So that makes all the math more complicated, but they're smart and they figured things out. They also, an interesting feature here is they actually have in parallel strided convolution and also max pooling. So they kind of do these 2 operations in parallel to downsample images and then concatenate it again at the end. Another thing is they're really going all out on these efficient convolution tricks that we talked about a couple lectures ago. So as you can see, they've actually have these asymmetric filters like 1x7 and 7x1 convolutions. They also make heavy use of these 1x1 convolutional bottlenecks to reduce computational costs. So this is just the stem of the network. And actually, each of these parts is sort of different. So they've got 4 of these inception modules, then this downsampling module, then 7 of these guys, and then another downsampling module, and then 3 more of these guys. And then finally, they have dropout and a fully connected layer for the class labels. So another thing to point out is, again, there's no sort of fully connected hidden layers here. They just have this global averaging to compute the final feature vector. And another cool thing they did in this paper was inception resnets. So they proposed this residual version of the inception architecture, which is also pretty big and scary. The stem is the same as before. And now these repeated inception blocks that they repeat throughout the network, they actually have these residual connections. So that's kind of cool. They're kind of jumping on this residual idea and now improved state-of-the-art on ImageNet. So again, they have many repeated modules. And when you add this thing all up, it's about 75 layers, assuming I did the math right last night. So they also show that between their sort of new inception, version 4 of Inception GoogleNet and their residual version of GoogleNet, that actually both of them perform about the same. So this is a top 5 error as a function of epochs on ImageNet. So you can see that the inception network in red actually is converging a bit faster, but over time, both of them sort of converge to about the same value. So that's kind of interesting. That's kind of cool. Another thing that's kind of interesting to point out is there's the raw numbers on the x-axis here. These are epochs on ImageNet. So these things are being trained for 160 epochs on ImageNet. So that's a lot of training time. But that's enough of current events. And let's go back to our regularly scheduled programming. So today, oh yeah, question?
Do you know how many parameters they had in that?
I don't know. I think it might be in the paper, but I didn't read too carefully. Any other questions on, yeah?
So the algorithm will drop out in the last layer?
The question is about dropout, whether it's only in the last layer. I'm not sure. Again, I didn't read the paper too carefully yet. But the link is here. You should check it out. OK. So today we're going to talk about two other topics that are sort of common things in research these days. So those are segmentation, which is this sort of classic computer vision topic, and also this idea of attention, which I think is has been a really popular thing to work on in deep learning over the past year, especially. So first, we're going to talk about segmentation. So you may have remembered this slide from a couple lectures ago when we talked about object detection that was talking about different tasks that people work on in computer vision. And we spent a lot of time in the class talking about classification. And back in lecture 8, we talked about different models for localization and for object detection. But today, we're actually going to focus on this idea of segmentation that we skipped over last time in this previous lecture. So within segmentation, there's sort of two different subtasks that we need to define, and people actually work on these things a little bit separately. The first task is this idea called semantic segmentation. So here we have an input image, and we have some fixed number of classes, things like buildings and tree and ground and cow and whatever kind of semantic labels you want. Usually you have some small fixed number of classes. Also, typically, you'll have a background class for things that don't fit into these classes. And then the task is that we want to take as input an image, and then we want to label every pixel in that image with one of these semantic classes. So here, we've taken this input image of these 3 cows in a field, and the ideal output is this image where instead of being RGB values, we actually have one class label per pixel. So we can do this on other images and maybe segment out the trees and the sky and the road, the grass. So this type of task is pretty cool. I think it gives you sort of a higher level understanding of what's going on in images compared to just putting a single label on the whole image. And this is actually a very old problem in computer vision. So this that predates sort of the deep learning revolution. So this figure actually comes from a computer vision paper back in 2007. That didn't use any deep learning at all. People had other methods for this a couple years ago. The other task that people work on is this thing. Oh, right. So the thing to point out here is that this thing is not aware of instances. So here, this image actually has 4 cows. There's actually 3 cows standing up and 1 cow kind of laying on the grass taking a nap. But here in this output, it's not really clear how many cows there are. These different cows, actually their pixels overlap. So here in the output, there's no notion that there are different cows. In this output, we're just labeling every pixel. So it's maybe not as informative as you might like. And that could actually lead to some problems for some downstream applications. So to overcome this, people have also separately worked on this newer problem called instance segmentation. This also sometimes gets called simultaneous detection and segmentation. So here the problem is, again, similar to before. We have some set of classes that we're trying to recognize. And given an input image, we want to output all instances of those classes. And for each instance, we want to segment out the pixels that belong to that instance. So here in this input image, there are actually 3 different people. There's the 2 parents and the kid. And now in the output, we actually distinguish between those different people in the input image. Which those 3 people are now shown in different colors to indicate different instances. And again, for each of those instances, we're going to label all of the pixels in the input image that belong to that instance. So these 2 tasks of semantic segmentation and instance segmentation, people actually have worked on them a little bit separately. So first, we're going to talk about some models for semantic segmentation. So remember, this is the task where you want to just label all the pixels in the image, and you don't care about the instances. So here the idea is actually pretty simple. Given some input image, this is the fun one with the cows, we are going to take some little patch of the input image and extract this patch that sort of gives local information in the image. Then we're going to take this patch and we're going to feed it through some convolutional neural network. This could be any of the architectures that we've talked about so far in the class. And now this convolutional neural network will actually classify the center pixel of the patch. So this neural network is just doing classification. That's something we know how to do. So this thing is just going to say that the center pixel of this patch actually is a cow. Then we can imagine taking this network that works on patches and labels the center pixel, and we just run it over the entire image, and that will give us a label for each pixel in the image. So this actually is a very expensive operation, right? Because now there's many, many patches in the image, and it would be super, super expensive to run this network independently for all of them. So in practice, people use the same trick that we saw in object detection, where you'll run this thing fully convolutionally and get all the outputs for the whole image all at once. But the problem here is that if your convolutional network contains any kind of downsampling, either through pooling or through strided convolutions, then now your output image will actually have a smaller spatial size than your input image. So that's something that people need to work around when they're using this type of approach. So any questions on this kind of basic setup for semantic segmentation? Yeah?
Like, isn't there cases when the patch of a cow doesn't allow to classify as a cow, for example, and you have to like take close patches to region or something?
Yeah, the question is whether that patch-wise thing just doesn't give you enough information in some cases. And that's true. So sometimes for these networks, people will actually have a separate offline refinement stage where they take this output and then feed it to some kind of graphical model to clean up the output a little bit. So sometimes that can help boost your performance a little bit. But just this raw input-output setup tends to work pretty well, just as something easy to implement. Yeah?
In practice, what is the receptive field that you need in order to get decent results?
The question is, how big of a receptive field do you need? I'm not sure exactly. Probably pretty big. Maybe a couple hundred, maybe 100 pixels, that order of magnitude. So one extension that people have used to this basic approach is this idea of multi-scale testing. So actually, sometimes a single scale isn't enough. So here, we're going to take our input image, and we'll actually resize it to multiple different sizes. So this is sort of a common trick that people use in computer vision a lot. It's called an image pyramid. You just take the same image, and you resize it to many different scales. And now for each of these scales, we're going to run it through a convolutional neural network that is going to predict these pixel-wise labels for these different images at these different resolutions. So another thing to point out here along the lines of your question, that if each of these networks actually has the same architecture, then each of these outputs will have a different effective receptive field in the input due to the image pyramid. So now that we've gotten these differently sized pixel labels for the image, then we can take all of them and just do some offline upsampling to upsample those responses to the same size as the input image. So now we've gotten our 3 outputs of different sizes, and we'll just upsample them and stack them. And this paper, this is actually a paper from Jan LeCun back in 2013. So they actually also have this separate offline processing step where they do this idea of a bottom-up segmentation using these superpixel methods. So these are these sort of more classic computer vision image processing type methods that actually look at the differences between adjacent pixels in images and then try to merge them together to give you these coherent regions where there are not much change in the image. So then this method actually takes, sort of runs the image offline through these other more traditional image processing techniques to get either a set of superpixels or a tree saying which pixels ought to be merged together in the image. And they have this somewhat complicated process for merging all these different things together. Because now we've gotten this sort of low-level information saying which pixels in the image actually are similar to each other based on sort of color and edge information. And we've got these outputs of different resolutions from the convolutional neural networks telling us semantically what the labels are at different points in the image. And they actually explore a couple different ideas for merging these things together to give you your final output. So this actually also addresses one of the earlier questions about maybe the conv not being enough on its own. So using these external superpixel methods or these segmentation trees is another thing that sort of gives you additional information about maybe larger context in the input images. So any questions about this model? OK. So another sort of cool idea that people have used for semantic segmentation is this idea of iterative refinement. So we actually saw this a few lectures ago when we mentioned pose estimation. But the idea is that we're going to have an input image. Here they've separated out the 3 channels. And we're going to run that thing through our favorite sort of convolutional neural network to predict these low-resolution patches, or rather to predict this low-resolution segmentation of the image. And now we're going to take that output from the CNN together with a downsampled version of the original image, and we'll just repeat the process again. So this allows the network to sort of, increase its effective receptive field of the output, and also to perform more processing on the input image. And then we can repeat this process again. So this is kind of cool. So if these 3 convolutional networks actually share weights, then this becomes a recurrent convolutional network, where it's sort of operating on the same input over through time, but actually each of these update steps is a whole convolutional network. So that's actually a very similar idea to recurrent networks that we saw previously. And the idea behind this paper, which was in, I think, ICML 2014, is that if you actually do more iterations of this same type of thing, then hopefully it allows the network to sort of iteratively refine its outputs. So here, if we have this raw input image, then after 1 iteration, you can see that actually there's quite a bit of noise, especially around the boundaries of the objects. But as we run for 2 and 3 iterations through this recurrent convolutional network, it actually allows the network to clean up a lot of that sort of low-level noise and produce much cleaner and nicer results. So I thought that was quite a cool idea, that sort of merging together these idea of recurrent networks and sharing weights over time with this idea of convolutional networks to process images. So another very well-known paper for semantic segmentation is this one from Berkeley that was published at CVPR last year. So here it's a very similar model as before, where we're going to take an input image and run it through some number of convolutions and eventually extract some feature map for the pixels. But in contrast, the previous methods all relied on this sort of hard-coded upsampling to actually produce the final segmentation for the image. But in this paper, they proposed that, well, we're deep learning people. We want to learn everything. So we're going to learn the upsampling as part of the network. So their network includes this, at the last layer, this learnable upsampling layer that actually upsamples the feature map in a learnable way. So yeah, so they have this learnable upsampling map at the end. And the way their model kind of looks is that they have this, at the time it was an AlexNet. So they have their input image running through many phases of convolution and pooling. And eventually they produce, at this pool 5 output, they have quite a downsampled image, quite a downsampled spatial size compared to the input image. And then their learnable upsampling upsamples that back to the original size of the input image. Another cool feature of this paper was this idea of skip connections. So they actually don't use only just these pool 5 features. They actually use the convolutional features from different layers in the network, which sort of exist at different scales. So you can imagine that once you're in the pool 4 layer of AlexNet, that's actually a bigger feature map than the pool 5. And pool 3 is even bigger than pool 4. So the intuition is that these lower convolutional layers might actually help you capture finer grained structure in the input image, since they have a smaller receptive field. So they actually, in practice, take these different convolutional feature maps and apply a separate learned upsampling to each of these feature maps, and then combine them all to produce the final output. And in their results, they show that actually adding these skip connections tends to help a lot with these low-level details. So over here on the left, these are the results that only use these pool 5 outputs. And you can see that it's sort of gotten the rough idea of a person on a bicycle, but it's kind of blobby and missing a lot of the fine details around the edges. But then when you add in these skip connections from these lower convolutional layers, that gives you a lot more fine-grained information about the spatial locations of things in the image. So adding those skip connections from the lower layers really helps you clean up the boundaries in some cases for these outputs. Question?
How do they classify like accuracy, like compared to ground truth?
So the question is how to classify accuracy. I think the two metrics people typically use for this are either just classification, because you're classifying every pixel. So you can use classification metrics. Also, sometimes people use intersection over union. So for each class, you compute what is the region of the image that I predicted as that class, and what was the ground truth region of the image that had that class, and then compute an intersection over union metric between those two. I'm not sure which metric this paper used in particular. So this idea of learnable upsampling is actually really cool, and since this paper has been applied in a lot of other contexts, because we've seen that we can downsample our feature maps in a variety of different ways, but being able to upsample them inside the network could actually be very useful and a very valuable thing to do. So this sometimes gets called deconvolution. That's not a very good term, so we'll talk about that in a couple minutes, but it's a very common term. So just to recap, sort of when you're doing a normal sort of stride 1 3x3 convolution, we have this picture that should be pretty familiar by now. That given our 4x4 input, we have some 3x3 filter, and we plop that 3x3 filter over part of the input, compute a dot product, and that gives us one element of the output. And now because this thing is stride 1, to compute the next element of the output, we move the filter over one slot in the input, again compute a dot product, and that gives us our one element in the output. And now for stride 2 convolution, it's a very similar type of idea, where now our output is going to be a downsampled version, a 2x2 output for our 4x4 input. And again, it's the same idea. We take our filter, we plop it down on the image, compute a dot product, and that gives us one element of the output. The only difference is that now we slide the convolutional filter over 2 slots in the input to compute one element of the output. The deconvolutional layer actually does something a little bit different. So here we want to take a low resolution input and produce a higher resolution output. So this would be maybe a 3x3 deconvolution with a stride of 2 and a pad of 1. So here, this is a little bit weird. You know, in a normal convolution, you imagine you have your 3x3 filter and you take dot products on the input. But here, you want to imagine taking your 3x3 filter and just copying it over to the output. The only difference is that the weights, like this one scalar value of the weight in your input, gives you a weight for that. You're going to reweight that filter when you stamp it down into the output. And now when we stride this thing along, we're going to step 1 step over in the input and 2 steps over in the output. So now we're going to take the same learned convolutional filter, and we're going to plop it down in the output. But now in the blue, so we're taking the same convolutional filter, and we're plopping it down twice in the output. The difference being that the red box, that convolutional filter is weighted by this scalar value in the input, and for the blue box, that convolutional filter is weighted by the blue scalar value in the input. And where these regions overlap, you just add. So this kind of allows you to learn an upsampling inside the network. So if you remember from implementing convolutions on the assignment, this idea of sort of especially striding and adding on overlapping regions, that should remind you of the backward pass for a normal convolution. And it turns out that these are completely equivalent. That this deconvolution forward pass is exactly the same as the normal convolution backward pass, and the deconvolution backward pass is the same as the normal convolution forward pass. So because of that, actually the term deconvolution is maybe not so great. And if you have a signal processing background, you may have seen that deconvolution already has a very well-defined meaning, and that is the inverse of convolution. So a deconvolution should undo a convolution operation, which is quite different from what this is actually doing. So probably better names for this instead of deconvolution that you'll sometimes see would be convolution transpose, or backward strided convolution, or fractionally strided convolution, or up convolution. So I think those are all kind of weird names. I think deconvolution is popular just because it's easiest to say, even though it's maybe less technically correct. Although actually, if you read papers, you'll see that some people get angry about this. It's more proper to say convolution transpose instead of deconvolution. And this other paper really wants it to call it fractionally strided convolution. So I think the community is still deciding on the right terminology here, but I kind of agree with them that deconvolution is probably not very technically correct. And this paper in particular has a whole, they felt very strongly about this issue, and they had a one-page appendix to the paper actually explaining why convolution transpose is the proper term. So if you're interested, then I would really recommend checking out that. It's a pretty good explanation, actually. So any questions about this? Yeah?
Idea how fast there is this network is going to be relative to the patch-based?
I think, so the question is how much faster is this relative to a patch-based thing? The answer is that in practice, nobody even thinks to run this thing in a fully patch-based mode, because that would just be way, way too slow. So actually, all of the papers that I've seen do some kind of fully convolutional thing in one way or another. Actually, there is sort of another trick instead of upsampling that people sometimes use, and that is that, so suppose that your network is actually going to downsample by a factor of 4. Then one thing you can do is take your input image, shift it by 1 pixel, and now run it through the network again. And now you get another output. And you repeat this for sort of 4 different 1-pixel shifts of the input. And now you've gotten 4 output maps, and you can sort of interleave those to reconstruct an original input map. So that's another trick that people sometimes use to get around that problem. But I think that this learnable upsampling is quite a bit cleaner. Yeah, question?
What alternative name for deconvolution do you prefer?
So I think deconvolution is really nice. It just rolls off the tongue. I think fractionally strided convolution is actually pretty cool. Right? I think it's the longest name, but it's really descriptive, right? Because normally with a strided convolution, you move x elements in the input, and you move 1 in the input, and you move x in the output. And here you're moving 1/2 in the input. You move 1 in the input, which corresponds to moving 1/2 in the output. So that captures this idea quite nicely. So I'm not sure what I'll call it when I use it in a paper. We'll have to see about that. But so despite the concerns about people calling it deconvolution, like people just call it that anyway. So there was this paper from ICCV that takes this idea of this convolutional / fractionally strided convolutional idea and sort of pushes it to the extreme. So here they took what amounts to 2 entire VGG networks flipped on their head. So this is, again, the exact same model as before. We want to input an image and output our pixel-wise predictions for the semantic segmentation task. But here we initialize with a VGG, and over here is an upside-down VGG, and it trains for 6 days on a Titan X. So this thing is pretty slow. But they actually got really, really good results. And I think it's also a very beautiful figure. So that's pretty much all that I have to say about semantic segmentation, if there's any questions about that. Yeah?
Is there a LaTeX package for making neural network figures? Or how is that done?
The question is, how is this figure made? The answer is, I took a screenshot from their paper, so I don't know. But you could try TensorFlow. We saw in the last lecture that lets you make figures, but they're not as nice as this. Yeah?
How do we get the training data of this?
Question is training data. Yeah, so there exist data sets with this kind of thing where I think there's a common one is the Pascal segmentation data set. So it just has ground truth. You have an image, and they have every pixel labeled in the output. Yeah, it's kind of expensive to get that data. So the data sets tend to be a little smaller. But in practice, there's a famous interface called Label Me, where you could upload an image and then sort of draw a contour around the image, or around different regions of the image, and then you can convert those contours into sort of these segmentation masks. So that's how you tend to label these things in a UI way. If no other questions, then I think we'll move on to instance segmentation. So just to recap, instance segmentation is this generalization where we not only want to label the pixels of the image, but we also want to distinguish instances. So we're going to detect the different instances of our classes, and for each one, we want to label the pixels of that instance. So these models end up looking a lot like the detection models that we talked about a few lectures ago. So one of the earliest papers that I know of so this is actually, I should also point out that this is, I think, a much more recent task. That this idea of semantic segmentation has been used in computer vision for a long, long time. But I think this idea of instance segmentation has gotten a lot more popular, especially in the last couple years. So this paper from 2014 sort of took this, they call it simultaneous detection and segmentation, or SDS. That's kind of a nice name. And this is actually very similar to the RCNN model that we saw for detection. So here we're going to take an input image. And if you'll remember, in RCNN, we relied on these external region proposals that are these sort of offline computer vision low-level thing that compute predictions of where it thinks objects in the image might be located. Well, it turns out that there's other methods for proposing segments instead of boxes. So we just download one of those existing segment proposal methods and use that instead. Now, for each of these segments, for each of these proposed segments, we can extract a bounding box by just fitting a tight box to the segment, and then crop out that chunk of the input image, and run it through a box CNN to extract features for that box. Then in parallel, we'll run through a region CNN. So here, again, we take that relevant, that chunk from the input image and crop it out. But here, because we actually have this proposal for the segment, then we're going to mask out the background region using the mean color of the data set. So this is kind of a hack that lets you take these kind of weird shaped inputs and feed it into a CNN. You just mask out the background part with a flat color. So then they take these masked inputs and run them through a separate region CNN. So now we've gotten two different feature vectors, one sort of incorporating the whole box, and one incorporating only the proposed foreground pixels. We concatenate these things, and then just like in RCNN, we make a classification to decide what class actually should this segment be. And then they also have this region refinement step, where we want to refine the proposed region just a little bit. So I don't know how well you remember the RCNN framework, but this is actually very similar to RCNN, just applied to this instance simultaneous detection and segmentation task. So for this region refinement step, there's actually a follow-up paper that proposes a pretty nice way to do it. So here, this is a follow-up paper from the same folks at Berkeley, the following conference. And here we want to take this input, which is this proposed segment, and we want to clean it up somehow. So we're actually going to take a very similar approach, a very similar type multi-scale approach that we saw in the semantic segmentation model a while ago. So here we're going to take out our image, crop out the box corresponding to that segment, and then pass it through an AlexNet. And we're going to extract convolutional features from several different layers of that AlexNet. For each of those feature maps, we'll upsample them and combine them together. And now we'll produce this proposed figure ground segmentation. So this is actually kind of a funny output, but it's really easy to predict. The idea is that this output image, we're just going to do a logistic classifier inside each independent pixel. So given these features, we just have a whole bunch of independent logistic classifiers that are predicting how much each pixel of this output is likely to be in the foreground or in the background. And they show that this type of multi-scale refinement step actually cleans up the outputs of the previous system and gives quite nice results. Question?
Yeah. So in the upsample box, are you deconvolution? I mean, what are you doing there? You're just copying the values, or you're applying a deconvolution?